In the last decade, the narrative around computing has shifted. We've seen Apple Silicon and AWS Graviton dominate headlines, leading many to believe that ARM is inherently better or more efficient than x86. But if you talk to a CPU architect, they'll tell you something different. The instruction set architecture, or ISA, is just the language a chip speaks. It isn't the engine itself. Today, we're deconstructing the myth that ARM's success is purely due to its reduced instruction set. We'll look at how modern x86 chips have evolved to act like ARM internally, and why the real performance gains come from microarchitecture and manufacturing nodes, not just the dictionary of commands the processor understands. By the end of this, you'll see that the gap between these architectures is narrower than marketing suggests.
To understand the present, we have to look at the 1980s. This was the era of the RISC versus CISC wars. x86 is a complex instruction set computer, or CISC. It was designed when memory was expensive, so instructions were dense and varied. One command could do a lot. ARM, on the other hand, is a reduced instruction set computer, RISC. It uses simple, fixed-length instructions. Back then, RISC had a clear advantage. Simpler hardware meant less power and more speed. But as transistors became cheaper and smaller, the lines began to blur. Intel and AMD didn't just sit still, they started stealing the best ideas from the RISC world. What we see today is a convergence, where the complex part of x86 is mostly a front-end wrapper for a high-speed internal engine. This is the most critical technical detail. Modern x86 processors are actually RISC chips on the inside. When an x86 instruction enters the CPU, it hits a component called the decoder. This decoder breaks down that complex x86 command into several small, simple micro-ops. These micro-ops look exactly like RISC instructions. This is why the CISC label is misleading today. Yes, x86 has a decoder tax. It takes more transistors and power to translate those complex instructions compared to ARM's simple ones. For a long time, people thought this tax was a deal breaker for efficiency. But in a massive 100-watt server chip, the decoder tax accounts for less than 5% of the total power. The real power consumption happens in the execution units in the cache, which look nearly identical regardless of the ISA.
If the ISA doesn't matter that much, why is ARM winning in efficiency? The answer is microarchitecture. When Apple designed the M1, they didn't just use ARM, they built an incredibly wide execution engine. They have 8 wide decoders and a massive reorder buffer that allows the chip to look way ahead in the code to find tasks it can do in parallel. Intel and AMD have historically focused on high clock speeds for legacy software. High clock speeds require deeper pipelines, which generate more heat and consume more power. Apple and others took the wide and slow approach, doing more work per cycle at a lower frequency. This is a design philosophy choice, not an ARM requirement. You could build a wide and slow x86 chip that matches ARM's efficiency, but you'd have to sacrifice the high single-core clock speeds that gaming and older apps rely on.
Another factor is the on-core and the manufacturing process. ARM chips often integrate everything onto a single die, the CPU, GPU, and memory. This is called a system on a chip, or SoC. By putting memory right next to the CPU, you save a massive amount of power that is normally wasted moving data across a motherboard. Furthermore, ARM designers like Apple and TSMC have had a lead in the nanometer race. A 3-nanometer x86 chip will always be more efficient than a 7-nanometer ARM chip, all else being equal. We are seeing this now as Intel moves to more advanced nodes and adopts tiled architectures. The efficiency gap is closing because the physical manufacturing is catching up, proving once again that the instruction set was never the bottleneck. So why does the myth persist? Because ARM allows for a clean slate design. When you license ARM, you aren't burdened by 40 years of x86 backward compatibility. You can build a chip optimized for today's workloads: video encoding, machine learning, and web serving. But don't count x86 out. Its weakness, complexity, is also its strength. The massive ecosystem of software and the sheer brute force performance of high-end x86 cores still lead in many heavy-duty workstation and server tasks. The real winner isn't ARM or x86. The winner is vertical integration. When the person designing the software also designs the chip, they can make optimizations that no generic ISA could ever provide. ARM isn't a magic bullet. It's a well-designed, modern instruction set that happens to be at the heart of some incredible engineering from companies like Apple and Amazon. x86 is a survivor that has successfully navigated the transition into the modern era by essentially becoming a RISC chip in disguise. In the future, the ISA will matter even less as we move towards specialized accelerators for AI and graphics. The instruction set is just the interface. The real battle is in the silicon, the physics, and the software. Thanks for watching.